Okay, let's just look at the Archimedes principle in further details. Look at these figures, for example. We have like the buoyancy force working upward, okay, and is equal to the weight of the volume of the liquid or water displaced, and is calculated by the formula rho GV. If we just try to just analyze this formula in further details, F is equal to rho is all the time buoyancy force, or Archimedes principle, is the rho of the water, and G is the gravity acceleration, and the V is the water displaced. Okay, so if the weight of the body is equal to the, for example, force or the buoyancy force, if we have like a equilibrium, so weight is equal to the like a weight is equal to like a mg. So if we just gonna substitute mg in this formula on the left hand side, so and you can cancel out g from two sides, so you're just gonna have like the m is equal to rho of the water times the volume of the water displaced. So this is like a simple formula that you can easily memorize. It's very interesting that this formula is very similar to the like density formula. If you remember, the density m is equal to rho v, but in Archimedes principle or the buoyancy force, all elements of this kind of like the all parameters of this kind of like the formula comes from different sectors. M is the mass of the body, okay, the whole body. Rho is the rho of the water, and V is the volume of the water displaced. So just bear in mind. There are some examples here. For example, if you have the weight on a scale here, for example, if it's like the 5 kilograms, if you're just going to put it here, the like, for example, it becomes like a 2 kilograms, like the lighter, and the scale shows like the 2 kilograms less. Okay, so if that is the case, for example, if you have like a 5 kilograms here, but under the water, the scale shows this is like a 3 kilograms. Like, for example, let's say in this case, we have like a 2 kilograms. But the question here is that how much is what is the volume here? How much is the overflow? For example, if it's like the exactly at the top of here, and once we're just going to put it here, what is the volume in here? So this is like one question that we can discuss it later. And if you have like, for example, the body weight, buoyancy force all the time, if it's like the floating, they balance out each other. However, it sinks once the weight is like the heavier than the buoyancy force. For example, let's say like a sand, a heavy metal solid. Once you're just gonna throw it in the water, it can sink easily because the density of the materials is higher than that. However, you can see like a very large ship, they are not sinking in the water. Why? Because we just try to just respect this kind of like the volume, and we make the volume larger than the weight of that one. Okay, and they can balance the very heavy, like the mass of the like the ship. It could be like 100 tons, but the volume displaced, we can make it as a like the hollow, like the section, like this one. Can you see a ball like this one? This is like the sand. Is sank very easily and get to like the bottom of the like the water or the lake, whatever. But however, if you have like a ball here in this case, ball can be easily floated in the water because the volume, even the ball is like the metallic ball, for example, doesn't matter. It's whatever quality. If it's like very heavy from metallic ones, like the heaviest type of like the metal, it still doesn't matter. It depends on the like the volume or displace or the, for example, the hollow like the section can make it up and make it like the floating under the water. So this is a clear example about this one. So we're just going to discuss about this later. So this question is that, for example, if you have like the situation like this, so the question here is that the amount of the water overflowing from this kind of container, is less than 2 liters, exactly 2 liters, more than 2 liters, or cannot be determined very exactly. So this is like the question we're just going to discuss. The other things section is about the important application of the buoyancy. So we just discussed about this one. Plimsoll line is a very popular or the on ship hulls. You can see this kind of like the sign is called Plimsoll line. So you can see this kind of like the sign in on the ship hulls to indicate the maximum safe loading limits of the for any ship, and it exactly used the formula that of the buoyancy formula Either W is equal to rho water, G water of the volume displaced, or you can just use, if you can just cancel out G, you can just use this formula, M is equal to rho W volume to water displaced. However, depending on the situation, depending on the density of the water and the temperature of the water, we can have like a different situations in here. Why? Because depending on, for example, on like the heavier water with the, let's say, like the salty water, the density is different. And also depending on the temperature, for example, in North Atlantic, the temperature of the water is different, for example, from the tropical water, which is like the water close to the equator. So just bear in mind, if you're just going to have like a very, like in the cold water, the density might be different. And based on that, this formula is different. Just pay attention to this formula. Another like the thing that we're just going to use Archimedes principle is the work in submarines to be able, and the submarines are able to sink and rise to the surface based on the very simple of a relationship of this kind of like a buoyancy force. You can see here we have like the force, gravity force here working downside, and the buoyancy force working upside. Okay, and once, for example, a buoyancy force is greater than the gravity, for example, it just floats and it comes to the water surface. And once we just gonna, gravity is heavier than the buoyancy, it just sink and goes under the water. But how does that work? If we look at here, for example, look at this figure, for example, if this is like the submarine has got a like the ballast tanks here. Once they're just gonna dive, they fill all these ballast tanks with the water, and they becomes very heavy, and they're just gonna go down under the water, submerged. However, once they're going to be trying to just come up, they try to just fill this like a balance tank and fill it with the water, with the air. They have like a compressed gas. They can fill the compressed gas and release the like the water from this kind of like area, and it becomes like a lighter. And based on the buoyancy, for example, force is greater than the gravity. So because it's just going to be like lighter, and they can come and rising to the water surface. So that's like a principle of the submarines, how they're just going to work. And we discussed earlier about the temperature and the impact of the temperature of the density of the water. If the density of the water changes, it can have an impact on the volume of water displaced. Imagine, let's say in this formula, the mass of the floating body or ship, whatever we have is different, is the same. However, if depending on the temperature and depending on the salinity of the water, the density of the water changes, the volume of the water displaced will be changed as well. Okay, so imagine the density of the water decreases. For example, in this case, we have the variation. It decreases with the, for example, let's say with the temperature, with like the higher temperature, we have the minimum density of the water. If, for example, in the 0-degree temperature, we have like 1,000 kilograms per cubic meter for water. Once we're just going to get to like the maximum, like 100 degrees, it can decrease to 960 kilograms per cubic meter. So with whatever like the temperature, like for example, tropical water, if the temperature is around like the 30 compared to the Atlantic, like the water in ocean, the temperature might be 10 degrees or something less than that, we can have a lighter water. And in that case, that one decrease, and the water volume of the water displaced becomes like the increase, and it can go down to the water. So, and the same, if you're just gonna look at here, the salinity rate, for example, the salinity rate here, you can see it's just gonna change. So this like a graph shows both the salinity rate and also the temperature, for example, in this case. And once you can see the salinity rate on the right-hand side increases, for example, the density becomes like the heavier. Not like, for example, the saline is less in the water. For example, if you have like a fresh water, like the river or something, you can see here the density is like the less, so it's a lighter. So for the salt water is heavier than the fresh water. Just bear in mind. And okay, so that's like the discussion for this. So we're just gonna go and give some examples about this later on.